So in this lesson, we're going to talk about finding limits analytically, or what we call algebraically. So we've seen how when we have a graph, we can find a limit by going to a certain point on the graph. But now what we want to do is we want to find out how can we find that limit, that y value that it's getting to, without graphing. Can we just look at the equation? So the key is this, is the easiest scenario is if we can just plug in the x value. So if we have a graph that is approaching, let's say we have y equals x squared, and we're approaching an x value of 2. Well, the y value, as we'll see, is just going to approach 4 because we can just plug that in. That's what we call direct substitution. So, direct substitution says this: if we can plug the point in, the value of c, the limit is just f of c. The limit of f of x as x goes to c is just f of c. All right? And so let's see what that means. So here we have a graph of y equals x squared. Now again, we want to do this without the graph. So we see that as the x value approaches 2, as we're moving along this curve here and we're getting close to 2, well, the y value is getting close to 4. And we know that because 2 squared is 4, right? So there's no hole there. It's not a problem. That's kind of the key. So we're going to be thinking about this as, is it a problem to put 2 in there? No. So we can say this is just 2 squared. Just put the 2 in there, and you'll find out what the y value is. Okay, remember, we're putting an x value in, and a limit is a y value, in this case, f of 2. All right? So, some special little limits that are real simple. If we have here, if b is an integer, then the limit of b is b. It's not going to change. So if we say the limit as x goes to 3 of 5 is, well, there is no x value here. So the limit of 5 is 5. Okay, if we have the limit of x, if we have like a real simple function, our function is just x, not x squared or anything like that. As x goes to c, well, let's pick a c. Let's make this more specific. Let's make this like x goes to -2. Well, you can plug -2 in there. X is exactly, well, this is the function y equals x. So just plug in -2 into that, and we get -2. If we're talking about an exponent, or a power, I should say. So a power, x to some power, where n is just an integer. Well, we know that the graph of x to the n, or let's say x to the 5th, the limit as x goes to -7 of, oh man, why did I pick -7? Let's go a little simpler. -1 of x to the 4th. How about that? Okay, well, we know the graph of x to the 4th or x to the 5th or x, they don't have holes in them, okay? X to the 4th is kind of a flat looking thing like that, right? Okay, and so there's no holes. So we can always evaluate this. I'm going to plug in -1, and we get -1 to the 4th, which is just 1. Okay, so that's simple direct substitution, and that's so easy. We wish we could always use that, and that's going to be our goal, is to apply that. So we've seen that when we have some function and that function doesn't have any holes, or at least it doesn't have any holes or domain restrictions where we are looking, then we can just evaluate that limit by direct substitution, all right? So here, let's say we got some function f of x. The limit of f of x as x goes to 3. Well, that point exists right here, and so it's just 5. Now, that could actually be a hole as well, so we could put a little hole there, and if somehow we know the limit is of f of x as x goes to 3 is 5, then we can use that, all right? then we've got these properties. Let's stick with that there. All right, so if we want to find some multiples of this, we can do some things with this. So we've got some properties. The first property is what we call a scalar multiple. So if I have this same function that I just graphed up above, and I want to know what 3 times f of x is. Well, I know that the limit of f of x as it goes to 3 is 5. Well, if I got 3 times f of x, it's just going to be 3 times that, 15. All right. If I have two functions, let's say I have another function, g of x. All right. And let's say that I tell you, and we know that the limit of g is 2. Okay, so one function is going to 5, one function is going to 2. Well, we don't need to know the rest of the graph. We just know what they're going to. So we can say that if we want to add these functions, then the limit as x goes to 3 of each of these, of the sum of these two, remember f of x and g of x are just talking about y values. Well, we're just going to add those two y values. 5 plus 2 is 7. All right, so that's the idea. So you can just think of it as if this function or these functions have these points 3, 5, and 3, 2. And we can multiply them. We'd get 5 times 2 if we were multiplying the functions. We can divide them, and we can just treat that as a point. We can raise it to a power as well. So we'll see that more as we move on here. All right, but we'll keep those in mind. So we're going to look at some strategies here, all right? We have some ways that we can get rid of problems. So sometimes we have a function like this where we want to find a limit that as x goes to 2. But what happens when we plug 2 in here? So if we plug 2 in, we get 2 squared minus 2 times 2 all over 2 minus 2, which is 0 over 0. So that's a problem there, all right? So 0 over 0 is not a number. We can't use it. It's not 0. So what we need to do is we need to factor this. So if we factor this, we can take this function here, f of x, and let's see what happens if we factor this. If we take out an x on top, we're going to get something like this. X times x minus 2 all over x minus 2, or really just 1 times x minus 2. And these cancel. Now, I'm changing the function here. So I'm simplifying it here to x. So this really is a different function now. So we'll call it g of x. And so the idea is these are identical at all but one point. 2 is a problem here. You cannot plug in 2 here. 2 is not a problem here. But the limit of this is going to be the same as the limit as x goes to 2 of g of x, which is x. Well, that's not hard to compute. That's just 2, right? So the moral of the story is this. We're going to try to get rid of any problems or any domain restrictions so that we can just use direct substitution. All right? So that's called our limit replacement. If two functions are exactly identical except for one point, that at x, one value c, in this case 2, okay, and g of c exists, then we can find the limit of f of x by finding the limit of g of x, which is just g of c. In other words, we use direct substitution. All right? So we're going to have a few strategies here that we're going to see. Okay? We'll go through these kind of quickly. So we have our first strategy is factoring. So here we notice if you plug in 0, we get 0 on top and 0 on bottom. That's a problem. You can't plug in 0. So what we need to do is we need to factor. So we're going to factor the top here. And we get 5x plus 8. We're going to factor out x squared. Yep, and we'll leave it at that. On bottom, we can factor out x squared. And we get 3x squared minus 16. And so we haven't found the limit yet. We're just cleaning up this function. And we notice those x squareds cancel. And so the limit that we were starting with is the same as the limit of this. And we got to ask ourselves, can we just substitute here? Well, we can, right? 0 is not a problem anymore. So this is just going to be 5 times 0 plus 8, 3 times 0 squared minus 16, which is 8 over negative 16, which is negative 1/2. So we can't substitute here because we don't get a real number, but we can substitute here. All right, so our first strategy is to factor and simplify the function.